So let's get through chapter 3 today. Stoichiometry. That's kind of a big word. It simply means counting. What we want to be able to do with a chemical reaction, the expression of a chemical reaction. Remember, we've got the alphabet first, like hydrogen and carbon and oxygen and all those. That's the alphabet. Then we wrote words, compounds like water or table salt. Those are our words. And we're going to make sentences by the end of this chapter. And that's a chemical reaction. We're going to take products, reactants, and make products out of them. And that's a requirement before you can do the stoichiometry part. Stoichiometry is a big word that means if you put so much of the reactants in, how much product can you expect? To be able to calculate those values. All right, this is just a little history. It was German. So I'm not going to go any further with that. It's not enough time for it anyway. The problem we have in chemistry is that we see things, right? We see what we perceive to be the evidence of chemical reactions, like the evolution of a gas or generating heat or cold, or a solid precipitating out of a clear solution. We recognize those things on the macroscopic scale, but what's actually happening is on the microscopic, what we can't see. We're trying to get a handle on that because if you are unable to manage the microscopic world, then there's no way you can predict the outcome. So we've got this method called counting by weighing. And that's where dimensional analysis is going to be your best friend. So what do we mean by counting by weighing? Well, first of all, atoms are too small to count, right? So we're not actually going to count individual atoms. There's technology now where you can count individual atoms, but we don't have several $1 million for that instrument, and it takes too long anyway. So we use the method that was developed during the late 19th and 20th century. So we have to assume that every object, every molecule, every atom, whatever the case may be, if you're counting them in a mass, we know that there are billions and billions of atoms and molecules in any substance we can sample, large enough sample to actually weigh it on a balance. So one of the prerequisites is that we treat every object in that mass as being identical in size and weight. That's if they're pure, of course. They have to be pure in order to make that assumption. And then in order to count by weighing, we have to know the average mass of each one of those atoms, molecules. If we know the average mass, then we can use dimensional analysis to make the transition from weighing them to how many of them are there. Right? I'm going to show you how that's done. For this example, if we have a pile of marbles that are 394.80 grams, and we want to be able to estimate the number of marbles in that container, it should be fairly easy to sample 10 marbles out of that group and weigh them. So if we sample 10 marbles and they turn out to be 37.6 grams, then we can calculate an average mass for each marble. Right? So that's what we're going to do first. We get that average mass is 3.76 grams per marble. And then if the total mass is 394.8 grams, actually that's not written correctly, 394.8 grams is the total mass, and our conversion factor changes grams to numbers of marbles. Well, one marble weighs what? 3.76 grams. So that leaves us with marbles. That factor was left out of this calculation. And to the nearest whole marble, we get 105 marbles. Okay, so we've counted the number of marbles in that container by weighing them. Okay, we're going to do the same thing with atoms. So you're probably wondering, how do you weigh a single atom? Or how do you count enough atoms individually so that you can get an average weight for the atom? Well, we leave that up to the experts, those who do this for a living. Okay. And what we settled on is we pick one of the elements and we fix its mass as a certain value, and everything else is related to that. Now, that mass that we pick for it is not arbitrary, but the mechanics of getting at that mass are a little more than this course can handle. So I'm just going to tell you that the standard that we pick is carbon. Okay. And in fact, it's not just any isotope of carbon, it's the carbon-12 isotope. Actually, the most common isotope of carbon in a naturally occurring sample. And we fix its mass at 12 atomic mass units. Okay, that's our standard. And it has infinite significant figures. Everything else is ratioed to that standard. Now, years ago, oxygen was used simply because oxygen in nature, most everything, especially all the metals and many of the nonmetals, are combined with oxygen before you separate them. So we said, oh, oxygen might be a good idea. Well, the problem with oxygen is it's a gas, plus it's diatomic. So that messes with your calculations. So eventually they settled on carbon-12 as the standard. Now, what's an atomic mass unit? Well, to give you some intuition of what one atomic mass unit is, it's roughly the mass of a proton. Okay, or a neutron. So if we say carbon-12, we're saying that the average mass of all of those nucleons is 12, or 1 each. Okay. All right. Your textbook probably says atomic mass units with a U, but if you transition to, say, physics, U is going to mean something entirely different. So that's why I use AM, atomic mass unit. You can use U if you want to, but AMU is my preferred. Now, for our practical purposes as chemists, we know that carbon doesn't occur, and none of the elements occur in pure isotopic form. They occur in a mixture. So once we've identified the standard here is 12, and we compare all the other isotopes to that one, then those values are going to be not whole numbers. They're all going to be fractions, decimal fractions. And not only that, is naturally occurring elements are mixtures of isotopes. Okay, so that's why, well, I'm going to get ahead of myself. We also have carbon-13, and we have carbon-14 also, but it's radioactive and very minor components, so we usually don't consider that one. So carbon-13 would have a mass of 13 point something. And we get that the abundance of carbon-12 in nature is 98.89%. And then carbon-13 is 1.11%. Now, we might throw in 14 in here, but it's less than 0.01%. So we're not even going to consider that one. It's too small. Now, if this were my livelihood, I would consider every isotope that we could isolate and figure that into the mix. Naturally occurring carbon. Then I could calculate a weighted average for the atomic mass of carbon in nature. And that's what's reported on the periodic table in these numbers right here. That's why none of them are whole numbers, because they're all weighted averages. Okay, so how do we arrive at an average atomic mass for carbon of 12.01078? Well, we calculate, let's see, maybe I got it on the next page. I do have it on the next page. Okay. So what's 98? The contribution of carbon-12 isotopes is 0.9889 times 12. Right? I use the decimal fraction because percent is a dimensionless number. The decimal fraction gives me a value here of, let's see, does it say? Did I animate it? I didn't animate it. 0.9889 of 12. Is 11.8668. 11.8668 atomic mass units. That's what this isotope contributes to the overall. This one would be 13.034. 13.0034 atomic mass units compared to this one, right? Times what's 1.11 in decimal? 0.0111. I just move it 2 places to the left. 0.0111 times 13.0034. And this one contributes 0.14438 atomic mass units. So we just add those together. Let's see. Yep. Add them together, and I get 12.0111 atomic mass units. And this is, for our calculations, 12.0111 is the atomic weight of naturally occurring carbon. Now, this value is a little bit lower because we've included other isotopes, right? So this is not exactly the same. We're going to use those values. In fact, when we do calculations using these values, we're only going to use 2 decimal places. Like that. One of the reasons for that is that every so often, every 10 years or so, these periodic tables are updated with new values. And even more decimal places than that in complete lists for researchers. But one thing that never changes now is that second decimal place. Right? We round it off to the second decimal, and it's there, and it's going to be there forever. They only refine their values to like the 5th and 6th and 7th decimal places, so we don't have to worry about it. Okay. So here's a question. Knowing what we know now about how atomic mass is calculated, average atomic mass is calculated and reported in the periodic table, if you were able to isolate one atom of carbon, what's the probability that its mass would be 12.01 atomic mass units? What's that thing that the music they play? Is it Jeopardy? I need to put that in here so we can play that while you guys are thinking. The probability of finding one atom with that mass is 0. That's an average. You won't find any atom with that value as its atomic mass. But when we're using it to do calculations, since we have billions and billions of them together, this works just fine. Okay, all right. Now this is just a artist's idea of a mass spectrometer. I don't know if you've ever heard of that device, but this is a magnetic sector mass spectrometer because of that thing right there, that magnet. If you have a charged particle moving through a magnetic field, its trajectory is going to be bent, right? If all the atoms of carbon are charged to +1, right? We hit them with electrons, and it knocks one electron off of each one. So you've got each one of your isotopes has a single charge. So the force that's applied to each one of those isotopes as it traverses the magnetic field is the same. It's based upon charge only. So if the force is applied to carbon-12 versus a carbon-13, which one's going to bend more? The lighter one. Like carbon-12 is going to bend more than carbon-13 or carbon-14. Okay, so that's why you get those split beams. And the detector will pick up, electronics are fast enough now they can pick up individual strikes, individual atoms striking the detector. Usually you don't have a detector plate like that. Normally what you have is a single detector, and they just scan the strength of the field. And that works the same way. But that's how they tell the relative abundance of each of the isotopes with a spectrometer like that. Now, there are other ways to do it. I used a gas chromatograph with a mass spec on the end of it as a detector, and it didn't use a magnetic sector. It used what's called a quadrupole. But it gave you the same results for a lot less money. Okay, let's see. I better stop digressing because I'm going to run out of time. An element consists of 62.6% of an isotope with mass 186.956 and 37.4% of an isotope with a mass of 184.953 atomic mass units. Calculate the average atomic mass. So if you guys calculate your grade point average for all your courses, that's what you do. It's a weighted average. So an A in a 3-hour course is worth a whole lot more than an A in a 1-hour course. That's what we're saying. So if we take 0.626 times 186.956 and then add that together with 0.374 times 184.953, we get an average atomic mass. And there's a strung out calculation, and it's 186.2 atomic mass units. So which element is that? Well, we know 2 ways to identify an element. If you know the atomic number, which is the number of protons. If you don't know that and you can't get it, the other possibility is the atomic mass, average atomic weight of naturally occurring elements. So we know 186.2, and as you go from top to bottom, left to right, those numbers also get bigger, right? So we just look along there, follow along until we get to 186.2. That's the closest one. It's bigger than that one, it's smaller than this one. It's got to be that one. So our element is rhenium. Now, you didn't have to memorize that one because you're probably never going to see it again. But that's how you identify your element if you don't have number of protons. All right. So we're going to transition from the atomic mass units to something more practical, because we're not going to be counting individual atoms. We're going to be counting billions of atoms. So we need a new unit of measure. And this is the international unit for counting stuff in chemistry, the mole. The mole is simply a number of things. I think I wrote it up on the board before. Like 1 mole equals 6.022 times 10 to the 23rd things. Atoms, molecules, ions, chickens, doesn't matter. It's the number of things. So in order to make the correlation between the mole, that number, and our standard average value for each of the isotopes, and using carbon-12 as our standard, of course, we define the mole as the number of carbon atoms that are contained in exactly 12 grams of carbon-12. So that number, and it generally goes out more decimal places than that, but this is enough for us. You're going to have that many atoms of carbon-12 will give you exactly 12 grams. Okay, so what that means is if we've got an average value for carbon of 12.01 atomic mass units per atom, you also have 12.01 grams per mole. So these values, they can either mean atomic mass units per atom or grams of that element, naturally occurring mixture of isotopes, that many grams per mole. That's the one that's going to be the most useful for us there, because we can measure grams in the laboratory. We can't measure individual atoms. Okay, this is also called Avogadro's number. Avogadro's number. Now, Avogadro didn't do this calculation. He is just honored with that name because Avogadro's theory in the gases led to the ability to determine the number. Right, we haven't got the gases yet, so we'll let that ride for now. Okay. All right, this is just a check. Why 12.01 grams per mole and not 12 grams per mole? Because it's a mixture of isotopes. All right. So here comes some more dimensional analysis. Say you have 4.48 moles of iron atoms. How many numbers of atoms do you have? Well, remember we have an equivalence. 1 mole equals 6.022 times 10 to the 23rd. So we can create a ratio or conversion factor, right? And if we have 4.48 moles, and in this case, it doesn't matter that it's iron atoms. That's superfluous. Don't need to know that. We just need to know what's the conversion. And this is atoms. So 1 mole, and we put, this is the numerator, remember? So that cancels, and this is 6.022 times 10 to the 23rd. So what would an estimate of that be? Well, let's see. That's about 5. It's about 3 times 10 to the 24th, something like that, in the neighborhood. Yeah, 2.7. So I got it within 1 order of magnitude. Anybody know do you know what an order of magnitude is? Okay, it's simply powers of 10. Right? If I have, say, 1 times 10 squared versus 1 times 10 to the 4th, this one is 2 orders of magnitude bigger, right? Because we stepped up to 3 and to 4. So that's 2 orders of magnitude, or 100 times. All right. Mass in grams of 1 mole of a substance. Okay. Nitrogen, if we look up there and round it off to 2 places, 14.01 is the molar mass for nitrogen. And that's another way we say the molar mass and how much does a mole weigh? Or what's the mass of a mole, molar mass? Sometimes I'll slip and use atomic weight. That's the way I learned it originally, but they've switched to molar mass, which is accurate. Weight's only good if you're on the surface of the earth. Okay, if we know we can find the molar mass of any element, naturally occurring element in the periodic table. But we have compounds, right? So how do you calculate the molar mass? A mole of, say, water. Well, if we put the mass of one oxygen, a mole of oxygen would be what? Look on the periodic table. It's 16 grams per mole, right? That's for oxygen. How about hydrogen? Right? This is going together into 1 mole of the compound. So 1 mole of water molecules has 1 mole of oxygen, but 2 moles of hydrogen. And hydrogen is 1.01 grams per mole. So that has to be multiplied by 2. So when you add those together, the molar mass of water is 18.02 grams per mole. That's how we determine. If you need the molar mass of a compound, you just add up the molar masses of every atom in the formula, excuse me. And if there's more than one of them, you multiply that value times individual. You just add them together. Okay? Now here's one where you could make a mistake if you're not careful. Barium nitrate, right? Barium is a huge atom. It's going to be 137.33. And how many nitrogens do we have? Well, we've got one nitrate with a parentheses of 2. So there are 2 nitrogens, 2 times 14.01, and 6 oxygens. Okay, then we add all those together, and we find that the molar mass of that compound, that formula, is 261.35 grams per mole. So if you have a mole of that formula, you'll have 261 grams. Okay. Now, when you read the side of a bottle, whatever chemicals in the bottle, it'll have printed on the outside a value that is the molar mass. And usually, instead of saying molar mass, they'll say FW, formula weight. The reason they do that is because molecules like water, carbon dioxide, sulfur dioxide, diphosphorus pentoxide, those are molecular compounds. In other words, they're bound into single units. But ionic compounds like barium nitrate, they're not, that's a formula. In actuality, it's a matrix of ions in the solid. So you don't actually have one barium nitrate here and another one here and another one here like that. They're just an array of positives and negatives. So we go to formula weight. This is the simplest expression of the ratio of barium to nitrate ions in that compound. So we use that rather than trying to say we have, I don't know, 15.77 billion bariums and then however many nitrates you have. It just doesn't make any sense. In technical terms, it's stupid. So which of the following is the closest to the average mass of one atom of copper? If you got this on a test, you would go straight to the correct answer, E, right? One atom of copper cannot weigh 10, 20, 30, 40, 50 grams. It's just physical impossibility. But you can calculate that value right? If you have one atom of copper, see, do we do the calculation here? Yeah, there it is. So this is a chained conversion. We've got one atom of copper. We want to convert it to moles because our value up here is grams per mole. If we want to find out what the mass of one copper atom is, then we need to convert to moles and then use the molar mass to convert to mass. So we use that first conversion factor, gives you moles, and the second conversion factor is 63.55 grams per mole, converts it to mass. And that's when you get 1.055 times 10 to the minus 22 grams. Okay. Number of copper atoms in, okay, this is sort of a trick question. How many copper atoms are in 63.55 gram sample? Well, that's the molar mass, right? So it's 1 mole or 6.022 times 10 to the 23rd copper atom. Okay. It was a trick question. All right. If we have 100 gram samples of each one of these elements, magnesium, zinc, and silver, what's the symbol for magnesium? Eng, okay. And zinc? Zn, yeah. And silver, that's the tricky one. Ag, from the Latin. Okay, we've got 100 grams of each one of those elements. Question is, which one has the greatest number of elements? Think of it this way. If I had gold coins and feathers, those two, and I had, say, 5 kilograms of each, which one would have the most number of things in it?
The one weighs less.
Yeah, the feathers, right? The feathers. So the one that has the smallest molar mass will give you the greatest number of atoms because it takes more of each one of those to make 100 grams. This is a test of intuition. So magnesium is 2431 on average, 2431 grams per mole. And zinc is 6538. And silver is a lot heavier, 107.87. And I'm rounding off to the 2 decimal places. Okay. So magnesium is going to have the largest number of atoms. If we put them in order from largest largest to smallest, we would have magnesium atoms would have the most, then zinc, and then silver would have the fewest number of atoms. There you go. Now we're going to change it up just a little bit. Let me leave that up there. We've got different masses. So now we have silver is 107.9 grams. Zinc is 70. Different sample size, 107.9, 21.0. 21.0 grams. We want to put these in order from ranking from greatest to least numbers of atoms. So the way I would approach this is, since we've only got 3 of them, we just need to find the one with the most atoms, the one with the least atoms, and then the other one goes in the middle, right? So the easiest way to deal with this is to say, how many moles of each? This one is greater than 1 mole, isn't it? Greater than 1 mole. But this one, that's less than a mole. And this is exactly 1 mole. So we know which one goes in the middle. Let's see, in order from greatest to least number. So this is the greatest number of moles is zinc. silver, and then magnesium. Okay. Come on. There we go. Check myself. Okay. The next problem is we're back to 100-gram samples, but of each of these compounds. We want to rank them from greatest to least number of oxygen atoms. And that's the reason I say Henry Ford. We're going to set up an assembly line. Right? If you've got, to answer your question, if you need to use the same operation for each one, then just set them up so that you can repeat the operation and then compare at the end. So we have water, laughing gas, right? Dinitrogen monoxide is nitrous oxide. C3H6O2, which is propionic acid probably, and then CO2. Okay, we have 100 grams of each. Let's see, I'm setting up my assembly line because we have exactly the same amount of each one. And we're going to use some dimensional analysis to find out numbers of oxygen atoms. Right? Do we have to go all the way to counting numbers of atoms? No, because we have a unit, the mole, which will do it for us. Right? So we need to get to moles of oxygen atoms. First of all, we need to convert this to moles of compound. Right? So we're going to do the same operation, only with different values in each of the conversion factors. Grams has to be on the bottom, right? Because it has to cancel. And moles on the top. And this is moles of compound. Right? That's moles of compound. So for each mole, what's the molar mass? We did this one already. 18.02. How about nitrogen monoxide? Well, it's 2 times 14.02 for the nitrogen plus 16, right? So far, so good. And it's 28.04. And then add 16 to it. Oops, hit the wrong key. 16. So 44.02. Okay. How about this one? 3 carbons. 12.01 times 3. Right? 6 hydrogens. Look up there. 1.01 rounded to 2 decimal places. Times 6. And add those together. And then 2 times 16 is 32. So this is 74.09. Okay. Now carbon dioxide. Carbon is 12.01. And 2 oxygens is 32. So that's 44.01. Okay. That gives us moles of compound. How do we convert that to moles of oxygen atoms? We're doing a chain conversion here. So we want compound on the bottom, oxygen atoms on the top. Right? This is going to cancel those moles. This is moles of compound, right? And this is oxygen moles on the top. So what's the ratio there? For every mole of compound, how many moles of oxygen do you have? 1 to 1, right? For every mole of that compound, you have 1 mole of oxygen. How about this one? Same thing. This one, 2 to 1. And 2 to 1. Okay, did I lose anybody there? Okay. So now that we've got moles of compound canceled out, we've got moles of oxygen. So now all we have to do is the calculation, right? We've done all the thinking. The rest is just crunching numbers. So if we start off with 100, divide by 18.02, right? And then times 1, that's 5.55. Let's see, did I keep the right? Actually, I could keep 4 significant figures, couldn't I? 5.549. Right? Because these are exact numbers. All conversion factors are exact numbers. So this is the only limit that I have. It's all multiply rules. So 5.49 moles of oxygen in 100 grams of that sample. Then we go back 100, 44.02 divide, and times 1 is 2.272. Okay. See what I mean by Henry Ford? I'm doing the same operation over again. In this one, well, Ford's a bad example. What did he say about his Model Ts? You can have any color you want as long as it's black, right? Okay, so, but in this case, we've got black, red, green, orange. Let's see, 174.09 divided into it times 2. Now this one is 2.699 moles of oxygen. And that's moles of oxygen in this sample of 100 grams of that compound. 44.01 divided into 100 times 2. 4.544. Okay. So now we're going to rank from greatest to least number. Greatest number. This one. That's number 1. Least number. This one. That's number 4. And then next one is this one. And the last one is that one. Okay. So it should be water, carbon dioxide, propionic acid, and Latin gas. There we go. That's how we solve that problem. Now, this is not the only place that we're going to use Henry Ford. There are other types of calculations that lend themselves to this method. But this is a good example. Stop me if you have questions or if I'm moving too fast. Okay. How do you solve problems? Did I mention this before? When you're confronted with a problem, say on an exam, you're given a word problem. Right? First thing you want to do is, what's the question? You got to know what the question is before you can get the answer. And then you look at the problem and say, all right, plot out a way to solve it. Is this a simple problem, like a one-step solution, or is it going to be complicated? Do I need to do several steps and then combine them? Or do I need like a chain conversion? How do you get there? And then go back after you get your answer and say, does this make sense? Now, I sort of skipped over that one on this problem because I've done it so many times. But we should do that. Do a reality check. Okay. Now we're talking about composition. How do we express the makeup of a compound? The bench chemist that is confronted with an unknown compound will do several things. If you're not told what the elements are in the compound, you got to find that out first, because that will dictate how you approach the analysis. So we have various instruments. There was wet chemistry in the past that you would test your compound for, and you go through like a decision tree and get down to say, okay, it has this element, this element, this element, this element, and nothing else. Now we can take that sample, dissolve it, put it through a spectrometer, excuse me, brain farts, through a spectrometer and determine the elements that you have. You can do that just qualitatively if you want. The spectrometers we have now will also do it quantitatively. But once you get the output from the analysis, one way to express it, and usually the way you express it, is mass percent. Mass of what element? Mass of this element versus the mass percent. So all the percents should add up to 100 or close within experimental error. And mass percent simply means mass of the element in the compound divided by the mass of the compound. Times 100. Forgot that. And by the way, what does this mean? It means parts per 100 parts. So what that means is this is a dimensionless number. It has no dimensions. If you say grams per grams, cancel out. So that's the danger with using percent. You need to know how is the percent calculated. So that's why when we say mass percent of something, we will say percent mass to nail it down. Or if you have percent composition in a solution, a liquid, like, I don't know, booze, right? Wine might be listed as 15% alcohol by volume, which means volume of alcohol per volume of liquid. Okay, so we have to specify what we mean by that percent. Otherwise, you can go off in any tangent. Okay, back to the question. If you're given mass percent composition, that's one thing. But we can also, if we know the formula of the compound, we can calculate its mass percent. So our example here is iron 3 oxide. Now, is that a type 1, 2, or 3 compound? You can tell from the Roman numeral, it's a type 2, right? The iron has possible multiple charges. So this iron 3 oxide, this has a 3 plus charge, this has a 2 minus charge. 3 times 2 is 6 minuses, and 2 times, excuse me, that's 3, is 6 plus, right? So it balances. Just checking ourselves. Okay, how do we calculate the percent? Since percent is a dimensionless number, we need to fix the amount somehow. So let's say we only have 1 mole of iron 3 oxide. How much would that mole weigh? Right, we would have 2 times iron, which is 5585 grams per mole. And 3 oxygens, 16. Okay, so if we add those together, 55.85 times 2, and 16 times 3 is what? 48. 48. We get 159.70 grams per mole. That is the formula weight for that compound. Now, if we want to calculate the percent of iron, right, we would just say, all right, if that's the total weight, how much of that is attributed to iron? That would be this right here, which is 111.7 divided by 159.7 times 100. And that would be 69.94%. 94% mass. Sometimes it'll be weight of iron in that compound. So that's how you would calculate from the formula what it is. Now, if you set up the problem and say like this times 100, the mass down here is 2 times your iron plus 3 times your oxygen, right? And up here, it's only 2 times the iron. So iron's going to appear in both of them, right? Don't put it up here and forget to put it down here. All right. So that's if you know the formula. I'm going to run out of time if I do this one. Let me see if it's animated. Let's see. Consider separate 100-gram samples of each of the following. Rank them from highest to lowest percent oxygen by mass. So we would just calculate the oxygen content of each 100-gram sample. In fact, 100 grams doesn't matter. If you're going percent is a dimensionless number. It doesn't matter if you have 100 grams or 200 grams. Once you have the formula, the 100 grams is irrelevant. So if we do that, we find out that percent. I did mention intensive versus extensive properties before, didn't I? I think I did. This is percent composition is an intensive property. That is, it doesn't matter how much you have. It's going to be the same number. It's like density and temperature. Doesn't matter how much you have, you're going to have the same value for any size sample. Okay. Unfortunately, we don't have enough time to do every one. Now we're going to go back the other direction. We're going to use percent composition now. Instead of knowing the formula, we're going to use percent composition to find out the formula. But it comes in 2 steps. And the reason for that is percent composition will only give you, with our calculations, the simplest whole number ratio of elements to one another, right? That may not be the formula unit. That may not be the molecular unit, but it's a start. And it's one step we have to do before we can get to the molecular formula. Once we get to the molecular formula, the way you do that, say, let's use this as an example. Say I have acetylene. We got any welders in here? Okay. Acetylene or benzene, right? Benzene is banned now because it's carcinogenic. You can still get it, right? But it's regulated. Notice that the ratio of carbon to hydrogen is exactly the same for both of them. They're 2 different compounds. Acetylene is nothing like benzene, right? Acetylene at room temperature and pressure is a gas. Benzene is a liquid. But the simplest whole number ratio is 1 carbon to every hydrogen. Okay? So how did we get there from here to here? From there to there, we introduced a factor of 2. So if this propagates through here, that gives us C2H2. But if we used a factor of 6, that gives us C6H6. So what we're looking for to go from the empirical formula to the molecular formula is this factor right here. Okay, the multiplier. So I'm going to show you how to get there in just a second. This is just an example of how we what's called a carbon hydrogen chain. If you know that your compound is only made of carbon, hydrogen, and oxygen, you can use this to analyze it for the composition of carbon and hydrogen, and then by difference, oxygen. because we're going to pump pure oxygen into our sample. We can't catch oxygen and weigh it, but we can catch the water in the first absorber, magnesium perchlorate, right? We weigh it before and weigh it after. That tells us how much water, which can be converted to how much hydrogen. Right? And then the second one is sodium hydroxide or some other absorbent of carbon dioxide, and that tells us how much carbon. And then once we find the mass of the carbon, we have the mass of the sample. Now we can calculate the mass of the carbon from carbon dioxide, mass of the hydrogen from water, and the difference is oxygen. And we can calculate for carbohydrates. We can, if all they have is carbon, hydrogen, oxygen, we can calculate their empirical formula. I've run one of these before. It's kind of fun, I guess. I don't think they use them much anymore. Okay. So we're going to use this as an example. We have adipic acid, right, which is one of the fatty acids that everybody's body has. Right? Remember, anybody had, I may have asked this before, A&P, anatomy and physiology. They talk about true fats. They did talk about it. Oh, okay. A true fat is a triester of glycerol. Glycerol is simply a 3-carbon molecule. Right? And these are hydrogens. And this is an alcohol group on the side. And then your fatty acid comes in with its carboxylic acid. Like that, has this long chain out here. And it forms an ester. So what it does is it gets rid of H2O, water, known as a condensation reaction, and forms a bond between this carbon and that oxygen. So after that happens, we get like that. And that's only one of them. A true fat has 3 of them. So this is known as a triglyceride. Okay. So adipic acid is one of those fatty acids that can be added to the glycerol and make a true fat. So the adipic acid has been analyzed by mass to show 49.3% carbon, 49.3% by mass. Right. Hydrogen is 6.9%. And oxygen then should be what's left over, the difference, 43.8%. Okay, so if we add these together, should come up to 100% or close to it. Okay, we're also told that the adipic acid was determined by some alternate method. The formula weight of adipic acid is 146 point nothing grams per mole. Hold on to that one, we'll need it later. For now, we're going to determine the empirical formula. What is the molar ratio of each of the atoms in that molecule? Okay, that's a dimensionless number, right? It's not grams. We can't convert it to moles unless we know what this means, parts per 100. If this is parts per 100, that's 49.3 grams per 100 grams. So let's say our sample is 100 grams, right? For a 100-gram sample, this is going to be 49.3 grams of carbon and 6.9 grams of hydrogen and 43.8 grams of oxygen. Now we're off to the races. We can convert this number of grams of carbon to moles of carbon, right? All we need is the molar mass of carbon. Grams on the bottom, moles on the top, right? Because the grams have to cancel and leave us with moles. All right, so carbon is 12.01, hydrogen is 1.01, and oxygen is 16. rounded off to 2 places. Okay. Now I'm not going to chain these all together because I want to look at the ratios. I want to ratio the moles of each one. And so I'm going to do this calculation first. 49.3, 12.01. So that's 4.105, 4.105 moles of carbon. And 6.9 divided by 1.01 is 6.832. Okay. And oxygen is 43.8 divided by 16, which is 2.738. Okay. First thing you notice is those are not whole numbers, right? I mean, we could write a formula, right? Carbon, hydrogen, oxygen with those numbers in subscripts, but we want the whole number ratio, right? Because we're talking about atoms to atoms. So how do you get that? This ratio is fixed now. It's always going to be 4.1 to 6.8 to 2.7 moles of each, right? Just like that. So if I recall, math says that if I divide everything through by the same number, I've still got the same ratios, right? So pick the smallest one. Okay, and divide those through by that number. That was 1, obviously. 6.832. Let me just do that, and then, oops, let me go back. There we go. 2.496. 2.496. And 4.105. Let's see, let's roll that one down and put in 2.738. And I get 1.499. 1.499. Okay. Now we're at the point where we can start estimating, right? This is very close to 1.5. This is very close to 2.5. And this is equal to 1. So now we're getting close. How do you get those now to be whole number ratios? Instead of dividing now, what if we multiply? How do you turn a half into a whole? Multiply by 2, right? If it's like this, just multiply by 2 and we get a 1. Okay. So since these are halves, multiply by 2. There we go. So that's going to be, and we can't reduce them any further, right? There's nothing that'll divide into those evenly. So now we have carbon, hydrogen, and oxygen at 3, 5, and 2. That's the empirical formula. Simplest whole number ratio of atoms in that unit. So what we're looking for is there a multiplier that we need to apply to this? Well, what's the molar mass of this formula? Right. Just say 3 times 12.01. And then 5.05 for hydrogen. Right, 5 times 1.01. And then 32 for oxygen because it's 2 times 16. And this formula weight here is equal to 73.08. Okay. Now, we know the molar mass for this compound. We found it by alternate methods. And we'll get to some of those second semester. 146 grams per mole is the true formula weight for the whole molecule. So that's not quite there, is it? So what value, if we multiply by 1, that won't get us there. What if we multiply by 2? 146.16 times 2, 146.16. That's really close. So I think this one should be 2, don't you? So now the molecular formula will be C6H10O4. Okay. Now I did that by saying what if 1, 2, and we could have gone to 3, 4 if we had to. But the simplest way to do it is to once you've got your empirical formula, find the formula weight for that, and then you get your molecular formula and divide it by that number. And the closest whole number you get is N. So if we had divided this by that, we would have got 2. Okay. All right. This is a chemical reaction. I'm going to run out of time. I can't go past 2 o'clock today, so I may have to finish this at home and splice it together. But there are previous semester videos if you want to get to it before I do. They just don't make the classes long enough. Or give us enough of them. You know, if we met 3 times a week instead of 2, that might fix the problem. And I can't talk less. That's a physical impossibility. Okay. This is a chemical reaction. Reactants on the left, products on the right, an arrow in the middle showing the movement, the progress from reactants to products. This C2H5OH is ethanol, right? The drinking kind. And then oxygen is the oxidizer. It's going to burn ethanol. Now this can happen in a flame or it can happen in your body. But in your body, this is an overall reaction. It just takes more steps. And the outcome, if the combustion is complete, will be carbon dioxide and water. And the way that reaction is written, it is balanced. And when we say balanced, we mean the same number of atoms of each element on the reactant side and the product side. So if we look, how many carbons do we have? We have 2 on the left. How about on the right? Well, once you write your compounds, you can't touch those subscripts. Those are chiseled in stone. Okay, so if we need 2 carbons on that side, we have to use a coefficient. Okay, you need 2 carbon dioxide molecules to give you 2 carbon atoms. And if we have 6 oxygens here, if we have 3 oxygens on this side, and now we have 4 or 5 on that side, we're going to need more coefficients, right? So I'll show you how to get there in just a minute. So if you just add them up to check yourself, we have 2 carbons, we have 6 hydrogens. Yep, 2 times 3 is 6. And we have 7 oxygens. So 2 times 2 is 4, and 3 is 7. So we're balanced. This can mean, when you have a balanced equation, this can mean one of 2 things. Right? 1 molecule of ethanol plus 3 molecules of oxygen yields 2 molecules of carbon dioxide and 3 molecules of water. Or you can look at it this way. 1 mole of ethanol plus 3 moles of oxygen yields 2 moles of carbon dioxide and 3 moles of water. That's the more practical approach. Now I'll just throw this in. This is a theoretical outcome. In other words, if we put something in here and we have enough oxygen to react with it, we'll get a certain amount here and amount here. And we approach it first at 100% efficiency. That never happens in real life. But that's our starting point. And we're going to introduce efficiency later. Okay, balancing equations. All right, these are the rules and helpful hints. And one of the documents I handed out, this one right here. This one has helpful hints. This is not a step-by-step. This is just things to be aware of that can help you reduce the anxiety and get you to the end quicker with fewer possibilities of mistakes. Now, when you read the textbook, they're kind of getting away from this, but some of them still do it. They'll give you an equation and say, then balance by inspection. And that's it. That's all they say. They tell you that it has to be equal numbers on either side. Of course, they tell you that. But then you balance by inspection, which means that they don't want to take the trouble to show you how to do it. So that's what I'm going to do. These are our helpful hints again. And I'm going to go through them in sample form. For now, you want your coefficients to be all whole numbers, simplest whole numbers. If I had put a 2, 6, 4, and a 6 here, that would not be the simplest whole number. I mean, the ratios would be correct, but it's not the simplest whole number. You can divide each one of them by 2 and get 1, 3, 2, and 3. That's what we're aiming for. Now, later on, I think maybe in the second semester, we're forced to using fractional coefficients occasionally. And we'll deal with that when we get to it. All right, I've got this one set up. Let me see. Let me skip that one now, and we'll come back to it. How about, I want to get one that's required some, oh, shoot. Okay, well, I guess we will do this one. All right, I've animated this one, so it'll. All right, so we're given. I'll tell you what. Yeah, just put this one on the board. I'll go to 2 o'clock and then we'll have to stop. Ammonium phosphate. Ammonium is a polyatomic ion, so it's a single unit with phosphate. Like that. I'm going to leave out any phases. Because at this point, they're not essential. But we know that these are the compounds. Reactants and the products yield that and ammonium chloride. Okay. Check to be sure all your compounds are written correctly. 3 minus charge, 1 plus charge, you need 3 of them to balance. 1 minus charge, 2 plus charge, you need 2 of those. Right. 2 plus charge and a 3 minus charge, cross multiply. Bring the 2 over here and the 3 over here. And then 1 to 1. Then you take an inventory. Now, if they're individual atoms in the molecules don't have any polyatomics, then this trick won't work. But if you have polyatomics in your reactants and products, and they remain intact through the reaction, so ammonium's here, ammonium's there, we didn't break it apart, so we can use it as a balancing unit or a group. So down this side, I put the balancing units here. And we have phosphate because it didn't break apart either. And I'm not going to put the charge because we just need to know the symbols. Calcium, chlorine. Then you do a tally, an original and initial counting. We have 3 of these, right? We have 1 of those, 1 of those, 2 of those. And the same thing over here. We have 3 calciums right here. We have 2 phosphates here. We have 1 ammonium and 1 chloride. There we go. So you can see right off that this is not balanced. 3, 1, 1, 2, 1, 3, and 2, 1. It's not balanced. So the next thing to do is say, all right, where do we start? This may take some practice and intuition. One place you don't want to start is if you have a single element in either side, on the reactants or product side. If there's a single element sitting off by itself, save it to last. Right? Because if you change the coefficient of that one, that's the only one you change. And then you don't have to go back through the whole equation and fix the rest of it. So save the single elements to last. And then if I can't figure out where to start, I just start at the first one. Let me see how I did it here. We've got to get the tally first. 3, 1, 1, 2. Yep. And then 1, 2, 3, 1. Okay. Now, where am I going to start? Looks like I'm going to start with calciums. Okay. So 3 calciums over there. I need 3 over here. Calcium only occurs in one place, so I can put a 3 here. That makes 3 calciums there, but it also increases my chlorides to 6. Okay. So there, and chlorides to 6. Okay. Now I'm going to correct the chlorides on that side. I'm pretty sure that's where I'm going next. Yeah. I need 6 chlorides over here. And that changes my ammoniums to 6. So ammoniums here are 6. Okay. Okay, now I'm going to do the ammonium with a coefficient of 2. Because 2 times 3 gives me 6. Okay, but it also gives me 2 phosphates. And Shazam, we're balanced. 6, 2, 3, and 6. Okay. That's what I call my budget method. I don't think I stole that from somebody. I thought of it myself. Okay, let's finish the calculations. There we go. Okay, this just illustrates the fact that you need to get the simplest whole number ratio. Several of these might be right, but the simplest whole number ratio is preferred. Okay, I'm going to skip that. There's the answer. Subscript, okay, this is just cautions. Now, if sometimes to get as an intermediate step, you can use a fraction as a coefficient. And then once you get it balanced, you get rid of the fraction. That's also in the useful. Let's see. I got 10 minutes. You want to do one of those fraction ones? Yeah. Okay, how about propane? C3H8. We're going to burn it and cook a steak on the grill. And we should get carbon dioxide and water as our products. Okay, so what elements do we have here? Carbon, hydrogen, oxygen. That's it. Now we got oxygen here sitting by itself, so we're going to save oxygen till last. But first we need a tally. 3 carbons, 8 hydrogens, 2 oxygens. 1 carbon, 2 hydrogens, and 3 oxygens. Okay, so we can either do carbon or hydrogen. I'm going to go carbon first. So if we put a 3 here, that makes 3 carbons, and that makes 6 plus 1 is 7 oxygens. Okay. Now I want to do hydrogens. So did it change the hydrogen? Didn't change the hydrogens. I got 8 here, I need 8 over here. So hydrogen is only one place. So 4 here should give me 8 hydrogens. Now I have 4 plus 6, that's 10, right? 4 oxygens plus 6 oxygen is 10 oxygens. Okay. Now I want 10 oxygens on this side. This is not going to need a fraction. I thought I'd need a fraction for this one. Did I do something wrong? 3, 3, that's 6. 6 and 1 is 7. Okay. And 2 there. Because all I have to do now is put a 5 there. All right, that didn't work the way I wanted it to. Let's change this to let's go in your gas tank. Octane. Maybe I wrote that wrong. This is 18. I bet I did. I wrote propane wrong. That's what happened. Never mind. Let's go to this one. So yeah, 8 carbons, 18 hydrogens, 2 oxygens. 1 carbon, 2 hydrogens, and 3 oxygens. Okay, I'm going to go to carbon, do 8 here. That gives me 16, 17 oxygens. Okay. Yep. And then on this side, I need 17 oxygens. So how to get 17 out of 2? Use a fraction. 17 halves. Right. If you got the oxygen molecules like this, so if you have 17 of them, but you only want half of that, then you're only using those 7 or 17. Okay. To mess with your minds. If you've got a diatomic element and we only use half of them, then now we only have 1 times 17. Gives me 17 oxygens. Okay. Now that we've got our balance, 8, wait a minute, hydrogens, excuse me, 18. Oops, I'm jumping the gun. Sorry. You probably caught me on that already. So 18, I need 9 here. So that's 18. And now I got to recalculate. 9 plus 16 is 25. There we go. Now, to get 25 over here, I need 25 halves. There we go. Now to get rid of that, these ratios are fixed. 1 to 25 halves to 8 to 9. All we need to do now is multiply that whole thing through by 2. All right, this gives me 2, gets rid of that fraction, 16 and 18. So now the balanced equation with whole numbers is 2, 25, 16, and 18. So that's what happens in your engine when octane combusts, ideally. So that's using the fraction trick. If we're going to do stoichiometry, we need a unit of measure that is something we can do in the lab. And we don't measure moles in the lab. We don't measure numbers of atoms. That's how the reaction occurs, at the microscopic level. But what we observe and measure at the macroscopic level is mass. So we need a bridge between the two in order to do stoichiometry. And that's where molar mass comes in. Now, we know how to calculate molar mass. Whether it's an element or a compound, we use molar mass. So here we got steps again for stoichiometric calculations. And they're up there, so they're recorded. but we're going to do an example. And if you like flow charts, there you go. Okay, let's consider this one. And this equation is already balanced. P4 solid, which is a very reactive form of phosphorus. This is white phosphorus. And all you have to do is leave it out in the air and it'll react. In fact, used to be tons and tons of this stuff produced every year until the workers started going home ill and some of them died. And this is the gas. And this is going to produce P2O5. That's a solid, I think. Yeah, solid. Okay. This one is already balanced for us, and we can prove it, right? 4 phosphorus, 2 times 2 is 4, and 10 oxygens, 5 times 2 is 10. So we know it's balanced. What we're given is 6.25 grams of phosphorus. Grams of that phosphorus are burned in the air, excess oxygen, all the oxygen you need. You're not limited at all by the oxygen. So all of this is going to be consumed. There's plenty of oxygen. Okay. What we want to know is what mass of oxygen is required to complete that reaction. Okay, here's how you do it. First of all, number one rule, there's a Great Wall of China. Right here. Here. Anywhere you've got an arrow or a plus sign, there's a Great Wall. You can't get over that wall unless you're in moles. You got to be moles. You got to be numbers. You can't get over there with mass. You can't go under, you can't go over. So we have to convert this to moles first before we can go anywhere in this reaction. So 6.25 grams of phosphorus is how many moles of phosphorus? Well, this is in the numerator, so we need grams in the denominator to get rid of the mass. But we leave ourselves with moles in the numerator. That tells you grams and moles in a quotient means molar mass. So what's the molar mass of P4? Well, we'll go over here and look at the phosphorus. It's 30.97 for 1. And you got 4 of them, right? So 28, 2 and 36 is 38, carry the 3, and 12 grams per mole for that formula. 123.88. There we go. So that will give us my calculator. That will give us the number of moles that we're going to react of P4. 6.25 divided by 123.88. And that's 5.04. I'm going to keep a decimal. Throw it out later. 10 to the minus 2 moles of P4. Okay. Now we can move. Now we can use our ratio. 1 to 4 to 5 is the ratio of moles. So this allows us moles of P4, moles of oxygen. That's the ratio of these two in this chemical reaction gives us our conversion factor. So we have one of these and 5 of those. So all I have to do is multiply this value in my calculator times 5. That cancels this one and leaves us with moles of oxygen. So that's 2.523 times 10 to the minus 1 moles of oxygen. Now that we got moles of oxygen, we have to convert back to grams because the question is mass of oxygen. We now know the moles of oxygen. We've got to convert this to mass of oxygen. So this is going to be moles on the bottom, grams on the top. Remember when I said these conversion factors are always equal to 1. Right? So if they're equal to 1, you can do them either way. In this case, we need moles on the bottom, so they'll cancel out, and grams on the top. So how many grams per mole of O2? 1 oxygen is 16. 2 oxygens is 32. Round to 2 decimal places. So that times the value is, and I'm going to keep 3 significant figures, 8.07 grams of O2 will be consumed in the burning of 6.25 grams of P4. Okay. That's how you do stoichiometry at our level. We're going to expand, but this is the beginning. If you've got grams to start with, convert to moles, and you can go over the top, convert to moles of either this reactant, or we could do it with the product too. We could determine how much product is going to be produced. All we have to do is change this conversion factor. Instead of 5 here, we'd have 2 P2O5. Then we could do that. Then we convert that P2O5 using its molar mass, and we can find out, theoretically, how much P2O5 would be produced. Okay. Questions or frowns? This one? This is the molar mass of phosphorus, and you've got 4 of them. So the molar mass of P4 is 4 times that, right? Okay. That's our first exercise in stoichiometry. This one is a little more involved. Let's see if I got time to do it. A little after 1. I should have enough time. This ups the game a little bit. So we've got 2 reactions, 2 separate reactions here. Methane in oxygen is burned to produce carbon dioxide and water. And in another reaction, ammonia is burned in oxygen to produce nitrogen monoxide and water. First thing we're going to do is write the balanced equations. Let's do that. Methane plus oxygen. So let's see, let me go over here. Yeah, let me do one over here and one over there. So here's the methane plus oxygen produces carbon dioxide and water. Okay. Yeah, I stretched it a little much. Let me back it up some. Need to leave room for the other reaction. There we go. And the other one is ammonia and oxygen. 2 separate reactions. Produce nitrogen monoxide and water. Yep. Okay, let's balance these equations. All right, since this is new to you, I'll go ahead and do the budget. Some of them, after you've done enough of them, some of them you can do without setting up the budget. I mean, you just obvious what happens. But in this case, we're gonna keep it legitimate. Carbon, hydrogen, oxygen. Those are the only 3. Not 1 carbon here, 4 hydrogens, and 1 oxygen, right? So that should be 6. 2. Oops. Let me spin. 6, 7. Ooh. Good thing I checked. Okay. On this side, we've got 1 carbon and hydrogens, 2 hydrogens and 3 oxygens. Okay, so carbons are already balanced. Okay, we're going to keep oxygen, so hydrogens are only option. So we need 4 hydrogens on this side. 2 times 2 is 4. We change the oxygens. 2 plus 2 is 4 oxygens. Okay. Now, all we need to do is have 4 oxygens over here. So 2 there gives us 4 oxygens. And that shows us we're balanced. Okay. Now I can erase it. Because I'm going to need this space down here for other stuff. Now that we've got a balanced equation, let's go balance this one. Nitrogen, hydrogen, and oxygen. 1 nitrogen here, 4 hydrogens, 2 oxygens. Here we have 1 nitrogen, 2 hydrogens, and 2 oxygens. I think that's right. 4, 5, 1, 2, 3, 4, 5. 1, 2, 6, 7. Yeah, that's right. Okay, nitrogens are already good. Hydrogens again. So we want 2 here. Right? That'll give 4 plus. Now we've got 2 oxygens and 1, so that's 3 here. All right. So how do we get 3 oxygens here out of that? Next trick. Intermediate step, use a fraction. Okay. So if we multiply this one times 3 halves, that should be 3 here. Okay, look at this. You got oxygen. That's the actual oxygen molecule. Got 2 oxygens. We only need 3 oxygen atoms, right? So if we multiplied that by 3, that would be 6, wouldn't it? 3 times 2 is 6. Well, let's take 6 and let's take a half of it. That's 3. Okay. So we've got 3 oxygen atoms using a fraction. Do I need to explain it a different way? Okay. Think of this as let's see. Okay, let's look at it as an algebra problem. Let's say we have 2 times x, and we want to end up with 3 on that side. Right, that's a valid algebraic expression, isn't it? Okay, so we know how to solve that, right? X equals 3 divided by 2, right? You didn't know there was so much algebra in chemistry, right? Thought you were out of when you got out of algebra class. Okay, that's not where we stop though, because we want whole numbers. This is an intermediate step. So now we have balance 3, 4, 1. We want to get rid of that half. This ratio is fixed: 1, 3 halves, 1, and 2. So as long as we, algebra again, as long as we do the same thing to both sides of the equation, then we're good. Multiply by something, divide by something. So what I'm going to do is multiply the whole thing times 2. So that'll preserve the ratio, right? 2 times 1 is 2. 2 times 3 halves is 3. 2 times 1 is 2, and 2 times 2 is 4. Okay, and we used our 2. So now the numbers are 2, 3, 2, and 4, instead of 1, 3 halves, 1, and 2. But the ratios are preserved. Mm-hmm. Oh, I'm sorry. Thank you.
So which one right?
I got to start over. Yeah, I have to start over. All that writing for nothing, man.
Well, I was gonna put it out, but I think you do what you do.
No, don't ever assume that. We'll start over again. Huh? Nitrogen, hydrogen, oxygen. Okay, now we have one nitrogen over here. Hydrogen's three here, and two there. And we have two oxygens here and two oxygens there. So we're back to hydrogens. Okay. We got hydrogen in one place here and hydrogen in one place there. It's a good thing we did that because now I get to show you another trick. If you've got hydrogen here as odd and hydrogen here as even, the best way is to use two coefficients and cross multiply. So we bring this 2 over here. And this 3 over here. That gives us 6 hydrogens here, and 3 times 2 is 6 hydrogens here. Then we have to do the rest of them. Right, so that's 2 nitrogens here, and still got 1 there. And this has, we did the hydrogens, 3 oxygens plus 1 is 4. Okay. Now, if those elements occur in more than one place on either side, then it's a little trickier. So now, let's see. We want 2 nitrogens on this side, so let's do 2. And that gives us 2 oxygens plus 3 oxygens, it's 5 oxygens. Okay. Now we use the fraction trick because you need 5 oxygens over here. 5 halves gives you 5 oxygens. Okay, now we can get rid of the fraction. Multiply it by 2 again. So that makes this one 4, makes that one 5, makes this one 4, and makes this one 6. Okay. All right. So let's clean up the mess. That one needs to be a 4. This one needs to be a 5. This one should be a 4. And this would be a 6. There we go. Now we've got balanced equations. We satisfied the first condition here. 6. And this one is 2, 2. Okay, that one's good. Now the question, what mass of ammonia would produce the same amount of water as 1 gram of methane? So we've got 1 gram of methane. And we don't know that. Now these reactions are occurring separately. We're only connecting them mathematically through the amount of water. We want to know what mass of ammonia is required to make the same amount of water as 1 gram of methane. So what we can do is find out how much water would this produce, right? And then say, okay, we want to make that same amount of water over here, and then back figure to this one. See where I'm going with this? All right. So 1 gram of methane, remember, can't go anywhere without moles. So what we've got to do is convert that 1 gram of methane into moles. So what's the molar mass of methane? Well, carbon is 1201. And 4 hydrogens. Hydrogen is 1.01 rounded to 2 decimal places. So that would be 4.04. 16.05 grams per mole. Is 6.231 times 10 to the minus 2 moles of methane. Okay, now we want to convert that to moles of water. All right, so I'm going to put it down here. There we go. And the ratio is we want moles of water and we've got moles of methane. That means methane has to be on the bottom because this is in the numerator. That has to be on the bottom. And the coefficients tell us that's 1 and this is 2. So I just need to multiply that value times 2. 1.4, oops, sorry. 246 times 10 to the minus 1 moles of water. That's the number of moles of water that this reaction will produce, 1 gram of methane.
And you took the 6.231 times 10 to the negative 2 to get, then divided it by the 2 to get,
Times.
you times it by the 2.
Yeah, because this is in the numerator,
Okay,
this is in the denominator. 2 times that gives you this value.
gotcha.
Now, the question is, how much of this, what mass of ammonia is required to give you the same number of moles, same amount, same number of moles of water that that reaction does? So now we've got, this is the same number of moles that we fit in here. So this goes in here, and we want to convert that to moles of ammonia. So we have moles of water on the bottom, because this is in the numerator. Moles on the bottom to cancel, and then moles of ammonia on the top. And what's the ratio? Well, in this case, 6 water and 4 ammonia. Coefficients, 6 and 4. Okay. So if I take that number times 4 and divide by 6, I get 8.31 times 10 to the minus 2 moles of ammonia. Okay. Question was, what was the mass of ammonia? Now we have to change it back to mass.
Hold on, please, for a second.
Yeah, sure.
And you took the 1.246
Mhm.
and you times it
Times that
by 4.
and divided by that. Yeah, this means times. This, just take this and put it right
Yeah.
there.
I was writing it on mine and I was making sure I was putting it right.
Okay. All right, so now to convert that to moles, we need molar mass of ammonia. Now we're going to take this times moles on the bottom, grams on the top, right? Because this is on the top. We want to cancel moles, leave grams. So what's the molar mass of ammonia? The nitrogen is 14.01 grams per mole. And 3 waters is 3.03 grams per mole. Add those together, we get 17.04. There we go. So if I multiply that times 8.31 times 10 to the minus 2, 4 times, I get, let's see, 3 significant, yeah, 3 significant figures. 1.42 grams of ammonia. So in separate reactions, we burn a gram of methane and 1.42 grams of ammonia, we get the exact same amount of water, mass of water. Let's see. How much of it did I put in here? There are the balanced equations. This gives us 0.1246 water. Yeah. That's the same as 0.1246 moles of water. And then we take that number of moles of water and convert it to moles of methane, which we did here. 8.31, yeah, 10 to the minus 2. And then convert that back to, oops, excuse me, to 1.42 grams of ammonia.
Now, where did you get the 30 from 30? Where did you get it from? I know you got.
Oh. Each hydrogen is 1.01 gram per mole. We got 3 of them. I did that one in my head.
Gotcha.
I just wanted to make sure.
Okay. That was a pretty tall order for your first jump into, or your second jump into stoichiometry. First one was fairly easy, straightforward. But this one stretched a little bit. Stretched a whole lot. The next concept is limiting reactants. In a chemical reaction, what we've done so far is we've balanced equations in the ideal. In other words, if we have a certain amount of A plus B as our reactant, it's going to produce a C plus D. We've got it set up so exactly the right amount of A and B are combined so there's nothing left here, and you produce only C and D. That's ideal. That's what we call a stoichiometric ratio. Exactly the right amount. As a practical matter in the lab, that never happens. For one reason, measurement uncertainty. You can never measure these exactly the right amount to give you a stoichiometric ratio. You can get close, but it's never exactly right. Simply because uncertainty is a fact of life. So we're going to get a handle on it by identifying limiting reactants. So what is a limiting reactant? In this reaction, let's say there's not enough B. Might be just a little bit less than we need. It runs out first, doesn't it? The limiting reactant always runs out first. And leaves some A behind. This is called the limiting reactant. This is called excess. In that previous reaction where we had phosphorus with oxygen, oxygen is excess. There's plenty of it. Phosphorus ran out, and that caused the reaction to stop. All right. This is some artist's idea of what's going on at the microscopic level. The stoichiometric mixture would have exactly the right amount of hydrogen combined with nitrogen. So the nitrogen is the blue, the double blue balls, and the hydrogen is these 3. So the ratio is 1 to 3, 1 here and 3 there. So that ratio, stoichiometric ratio, says for every 1 nitrogen, you need 3 hydrogens. And if you've got a matchup for every one, right, if that nitrogen has 3 dance partners, then it's going to produce 2 ammonias. This would be a stoichiometric ratio. There's nothing left over of these. You only have product. This is the case where the limiting reactant is hydrogen. Right? So we've got these 2 nitrogens sitting out there with nobody to play with. They got no dance partners. Right? So what happens to them? They're left over. They're in the product mixture. We have ammonia made from the others, but now we've got excess nitrogen, and the hydrogen is all used up. Okay. Let's see. Let's see how many more slides. I want to be sure. Yeah, I think we'll have time to run through this. So look at these different reactions. Where our reaction is hydrogen. This is a gas. plus oxygen yields water. And under standard conditions, that'd be a liquid. Okay, so that says that 2 moles of hydrogen plus 1 mole of oxygen gives 2 moles of water. Let's see if that's correct. 4 hydrogens, 4 hydrogens. 2 oxygens, 2 oxygens. Okay, so it's balanced. Now, if we look at this and say, all right, which one produces the greatest amount of product? Well, let's see, 2 moles. If we have 2 moles, this is A. If we have 2 moles of hydrogen and 2 moles of oxygen, how many moles of hydrogen can we produce? Well, what's the ratio here? The ratio is 2 to 1. Right? For every one of these, you need 2 of those. So one of these is going to consume all of those and leave 1 mole behind. And it will produce 2 moles of water with an excess of 1 mole of oxygen. Okay, so these will be in the product mixture. Okay, how about the second? So this one produced, the question is amount of product. Okay, so in this case, we produce 2 moles of product. That's all we're interested in. As the equation is written, we're interested in how much water is produced. That one produces 2 moles. Okay, in this one, we've got 2 hydrogens and 3 oxygens. Okay, here we are again. It only takes 1 of those to consume all of these and make 2 of those. And now we're going to have 2 moles of oxygen left over. So far, they're producing the same amount of product. 2 moles of hydrogen and 1 mole of oxygen. That's the stoichiometric mixture, right? 2 to 1, 2 to 1. So this is going to produce 2 moles of water. 3 moles of hydrogen, 1 mole of oxygen. 3 moles here, 1 mole there. Now we switched. This was limiting here, stoichiometric there. Now this one is limiting because 1 mole of this consumes 2 of those and we got 1 mole of hydrogen left over. But it still produces 2 moles of water. How about E? Oh. Each produce the same amount. Oh, well, that's it. All right. We can't just add the total moles of all the reactants to decide which reactant mixture makes the most product. What we have to do is decide which one is limiting and then base our calculations to produce products on that limiting reactant because it's going to run out. And when it does, the reaction stops. All right. We have examples and problems that you can work in the review document for limiting reactants. But I should have a slide in here and I don't. I should have a slide in here on how do you actually approach the solution of a problem where you're given mass of one and mass of the other. In fact, if you've got 2 reactants and you're given A grams of this one and B grams of that one, if you're given exact amounts of each one, you can assume that one of them's going to run out. So then you have to find out which one. Let me do percent yield. I think that's the last topic in this chapter. And if we have time, we'll work an example. Right? Otherwise, we'll have to wait until we look at the review documents and work those out. And in the meantime, you can go in there and work limiting reactant products and see how I did it with the handwritten version. And basically what we're trying to do is decide which one runs out. I'll give you a hint. If this is going to produce C and D, Then you take this one, convert it to moles and say, how much product will it produce? C or D, it doesn't matter. How much product will it produce? Right? Then you go in and do B and say, if this is all used up, how much product will it produce? And the one that runs out first is the one that produces the least amount of product. Then you can go back and say, okay, all our calculations now are going to be based on the limiting reactant, and it'll go from there. So that's where we're going with limiting reactant problems. Okay, percent yield. As a practical matter, you know, not only that one is going to run out, but there are other factors that are limiting the output of your reaction. And every chemical engineer knows that, and they try to get as much out of a reaction as possible. They know the theoretical limit. Right? We've already done that. And they know limiting reactants. But there are other factors that have to be considered, like you're going to end up with a mixture, and if you want one of those products out of it, you got to clean up the mixture. You got to extract it somehow, separate it from the other products. And that step itself will not be 100% efficient. You're always going to lose some somehow. That's one possibility, the cleanup step. The other possibility is you think that this reaction is going from these reactants to those products, but maybe your conditions are not as closely controlled as you think they are. And you actually produce side reactions, produce different products. And that bleeds off what you would expect. So that reduces your output. Right? Those two are major factors. And for a chemical engineer who's working for a company, it's all about, you know, the dollars. You make as much out of that reaction as you can and keep your bosses happy. That way you get to keep your job. So one way to express it is percent yield. If you have a theoretical yield, which you get from the balanced equation, right, we've done that. Then you actually run the experiment and you identify the amount of a product that's produced and compare those two, the actual yield to the theoretical yield times 100. The ratio gives you a percent yield. All right. Let's see. Here we got a problem. I think this is the last one. Yeah. So I think we got just enough time to do this one. So in this one, we've got P4 again. And we're going to react with fluorine, 6F2. It's already been balanced for us. Isn't that nice? 4PF3. So let's see, is that right? 4 P's, 12 fluoride. Yeah, we're good. That's a gas. Okay, that's the balanced equation. The question is, what mass is needed? What mass of that is needed to produce 85 grams of PF3? So this is the actual yield. You want to guarantee that you have that yield if you know that the reaction has been optimized to produce 64.9% yield. At 64.9% yield. All right. So we can't use this equation until we get the theoretical, because this equation is based upon the theoretical. So what we have to do is say, all right, how much theoretical yield do we need in order to work from this mass? So take the equation, and the equation says actual over theoretical times 100. In this case, it's equal to 64.9%. Okay. We know what the actual is, right? 85 grams. So now we have an equation in one unknown, right? And you can solve any equation in one unknown, you can solve it. So if we move this one to the other side, theoretical yield, and we have 85 grams over here times 100, right? And then this one, numerator here, denominator here, 64.9. Okay, then we do that calculation. Right, 85 divided by 64.9 times 100 is 130 point. Let's see. I'm going to keep a few decimals to avoid rounding errors. 130.7 grams. So that's the theoretical yield that we need to guarantee this much actual. And prove it to yourself. What's 64.9% out of 130.97? It's 85.0. Right. What's the fractional value? 0.649. So it's over half of this. So half of that would be like 65, 66. And then you go up another 10%. Yeah, it's pretty, estimating. It's pretty close. So now we're working from here. 130.97 grams. We want to convert that to moles because in this equation, we can't go anywhere without moles, correct? What's the molar mass of PF3? Well, let's see. Fluorine is 19.00. Rounded off to 2 places times 3. And then phosphorus is 30.97 times 1. Let's add those together. That would be the molar mass of PF3. Correct?
You don't add the 4.
Oh, no, not when we're doing these calculations. This is only for conversion factors. As far as calculations go, yeah. Good question. 30.97 plus. Okay, this is 87.97. So this, we need 87.97 divided into 130. Let's see. Yeah, it's already in my calculator. I just hit the button. 1.489 moles of PF3. So let's see, we have 1.489 moles of PF3. Now we want to use coefficients to convert PF3 to P4. We have 4 here and 1 there. So we just divide by 4. Okay. And I get 0.3722 moles of P4. Okay, almost there. Now we need the molar mass of P4. So let's see, this was phosphorus, wasn't it? So we need 30.97 times 4. Which is 123.88 grams per mole. And the next step is to take this value, moles of P4, and convert it to grams. So moles has to be on the bottom, grams at the top. And that's 123.88 times 0.3722, which is rounded off to, let's see, three significant figures. 4.6, excuse me. Standard notation. 46.1 grams of P4 will guarantee 85 grams of actual yield, considering 64.9% efficiency.
You were everyone.
Yeah, I know, I move all over the place. Are you writing it down though? Okay. And it's on video. You go back and look at it. Let's see if I did it right. Hold on a second. After all that trouble,
It-
there it is in steps. There we go, 46.1 grams. Sometimes I do these and I don't come out with the same answer. So then I ask myself, is it that or is it me? So then we go back through it and see, okay, find out where the mistake is. Sometimes it's me and sometimes it's that.
How do you even find which step you would have messed up on? Cause you're all over the place.
Yeah, that's a good point. I need to be better organized on the board, don't
Little
I? Yeah.
Oh, there's somewhere there, right?
bit.
Yeah, so what I did was we started here. And then we worked,
We started on the left.
We started on the other side.
well, yeah, we put that in there. And then we put this here at that percent.
Yeah.
And then we figured out, all right, here gives us the actual amount we need. I mean, the theoretical amount. And then we said, okay, how many moles is that? Okay, here's the moles of that. And then we say, okay, if that's the moles of that, then this calculates the moles of this. And then we take this moles of that, and that gives us the output. Sometimes I'm a little more organized than others. Today, I'm a little loopy. Okay, that's enough for today. Well, we'll